apologize for sake of time. I'm gonna go first. I'm gonna start with number 3, just because that was the one I was assigned and I need to get out of here. So, suppose translocation occurs between chromosomes 14 and chromosomes 21 in an individual. A translocation is a result of fusion between non-homologous, oh my gosh, I can't even say the word, chromosomes. Chromosome 14 is 109 million base pairs in length, while chromosome 21 is 48 million base pairs in length. For this problem, assume that the translocation fuses the entirety of chromosome 14 to the entirety of chromosome 21. Okay, so for letter A, we've got how long is the DNA portion of this translocation chromosome in meters. So for the when we added the 2 base pairs together, we're getting 157 million, which we are then going to times by our 0.34 nanometers, which is the length of a base pair, and then that comes out to 53,380,000, which we then times by 1 billion to get to our nanometers. We get times it by 1 billion nanometers to get to our 0.05338 meters. For letter B, it says how many nucleosomes are found within this translocation chromosome. Assume that the average length of the linker DNA is 50 base pairs. So we went with 146 as a nucleosome length, plus our 50 base pairs for the linker, which we divide our 157 million base pairs by our 196, comes out to 801,020 nucleosomes. For letter C, it asks how many H2A molecules would you expect to find with the translocation chromosome. So we take our nucleosomes times by 2 because there are 2 of each in a nucleosome. That comes out to 1,602,040 H2A histones. For letter D, it asks how many radial loop domains would you expect to find within this translocation chromosome. So if you remember from our the instructor notes, it gave us the range could be anywhere from 25,000 to 200,000 radial loop length for base pairs. So what I decided to do is I took the 157 million divided by both of these, comes out to 6,280 and 785. So we have a range of 6,280 to 785 radial loop domains within this translocation chromosome. Thank you very much.
All right, so before I start number 1, I'm going to do some explaining because we had a really, really hard time with this question, and the instruction notes really don't tell us anything to do with it. So this is our thinking. It may or may not be correct, but we feel like it's right. So to start off, I just drew basic examples of circular, DNA or RNA, doesn't matter, they both look the same, and then double-stranded and single-stranded. So this problem talks a lot about endonucleases and exonucleases. Right here, I just kind of gave a basic breakdown of what they are. Endo stands for inside, exo stands for outside, and then nuclease, it cleaves, nucleotides. So, starting with number 1. We have our first virus, which is resistant to exonuclease, but it's sensitive to endonuclease. So we figured if it's resistant to exonuclease, it's probably because it has no ending. So we decided it's circular, and it's sensitive to endo, which means it can just be cut anywhere. And we also decided that it's RNA just because it uses U rather than T. But we decided it was single-stranded. And if you notice right here, I put our adenosine, cytosine, guanine, and uracil levels. Now, because these are really close, it seems like it could be double-stranded, but we decided it was single-stranded because if you look right here, and you might not be able to see it that well, it doesn't matter too much, but if you have a complementary strand, which is what double-stranded is, then you should have exactly the same adenosines as you have of thymines or uracils, and it's the same with cytosine and guanine. You should have the exact same amounts. Not close, but exactly the same, which is why we put single-stranded on this one. Now for virus 2, we decided, because it's sensitive to both, we decided that, hold on, give me a second. Oh, that's why. I forgot to write whether it's circular or not. So first one was circular. The second one is linear. And we decided that because it is sensitive to both the endonuclease and exonuclease, we decided it was RNA because it used uracil rather than thymine. And we decided it was single-stranded just because the numbers were all over the place. For virus 3, we again decided it was linear. And the reason we decided that was because it's sensitive to both, which means endonucleases and exonucleases can cut into it. We decided it's DNA because it has thymine rather than uracil. And we also decided this one was single-stranded, again, because our values do not line up exactly. For adenosine, we have 20, whereas thymine, we have 18. And if it's double-stranded, they should both be exactly the same. So we decided single-stranded for that one as well. And then for virus number 4, we have resistant to exonuclease and sensitive to endonuclease. So we decided for this one that it's circular, for the same reason as we did for virus 1. And it's DNA because it uses thymine rather than uracil. And we also decided it was single-stranded just because numbers were all over the place, same as last time. For 2, I wrote the answers just so you can kind of see rather than trying to decipher from my voice. So for part 2A, we have topoisomerase 2 and nucleosome core particle. For part B, we have 2 and 0.34. Part C, we have topoisomerase 1. Part D, we have auric. Part E, we have 35 sulfur, 32 phosphorus. And for part F, we have RNA nucleoside and then DNA nucleoside.
Right, so for number 4, you pretty much do the same thing that you did in number 3. So number 4, we are given the total of 4,400,000, you know, the big number that's there. I don't want to say all of it. So I just wrote it in scientific notation just to make things smaller on the board. And since one base pair is equal to this, one base pair is 0.34 nanometers. And then I had to look it up online in order to find the conversion of nanometers to micrometers, because that's what we're looking for in these problems. So I got 0.001 is equivalent to 1 nanometer, so I plug that in, and you just, if you've done stoichiometry before in chemistry, that's pretty much just how this works. And I got 1,499, pretty much. The second one, you're actually looking for the circumference, or the diameter. And because in the first one you're looking at the whole linear length, it's pretty much the same thing for your circumference. It's just connected together instead of straight. So I took this and plugged it in here, and you can rearrange this to find the diameter. You just divide your circumference by pi, which is 3.14, and you come out to 477. For C, we're looking to find the loop domains, I believe, in micrometers. And pretty much the same setup. So in the equation, we're given that one loop domain is 50,000 BP. And then in the reading, if you look at it, it's telling you that one loop domain is equivalent to 300 nanometers because it's the combination of the 30 nanometer fibers altogether, which you just plug that in, throw in the micrometer conversion, and I got 26.46 micrometers. And then D, you're looking for the histone proteins, and pretty much the same setup. So you've got your entire length times we did 147 BP because it didn't specify if there was a 50 linkage area, 50 BP. So we just left with 147. You could do 146 because in the reading it says one or the other. It's between that. So we chose 147 just because. And then you multiply that by 8 because it's your 8 histine proteins. And it came out to 240,000 histone proteins. Right, and I'm also in charge of number 5. And since it's all pictures, we put it on here. for nucleosides. So you can kind of look at these and get kind of pretty confused of which one's which. But nucleosides, we know, have just sugars attached to them, nothing else. So if you look at these, you can see that this has got a sugar and a nitrogen base. And these ones have phosphate groups attached to a sugar and a nitrogen base. So therefore, nucleosides would look more like this, because they don't have the phosphates on it, which are A, E, and F, that you can see here too. Which leaves our nucleotides, which have a phosphate and a sugar attached. So you see all these phosphates and all these phosphates, and there's a phosphate here. So B, C, and D will be your nucleotides. For the next one, we're looking between ribose and then deoxyribose. So ribose actually has two OH that you can see on here. I feel really bad if you can't see this, but you can look it up on your thing. Because deoxyribose means that it's missing an oxygen, so therefore it only have one OH. So ribose has both two OH, you can see here and here, and here and here. So we got A, C, E, and F have ribose, and then your deoxyribose, you can see it only has one OH, so that's your B and D. And the last one, your pyrimidines, not sure how you say that. Your pyrimidines are only single ring structures. Those are your, like guanine, acidine, those things. So your single ring, this is a double ring, so that's a double ring, so that's not. So this is what we're looking for pyrimidine, is a single ring nitrogen base. So that would be your C, D, E, and F. And that's what we got for this.